So we see here that a mass attached to a spring has an equilibrium position. When a spring's position is referred to as equilibrium, it means that that is its position when it is at rest, when it's not being stretched or compressed. So we have a spring here. Just do something here. We have a spring here, and it's x equals to 0, right? It's at equilibrium, and it has been displaced to position x, right? It has been probably stretched or compressed to position x, and it exerts a restoring force of negative 5x dynes. So when a spring is stretched or compressed, it wants to go back to its original position. That force that tries to take it back to its original position is called the restoring force, and it usually has a negative sign because it is working against the stretching force or the compressing force, whichever the case may be. So it always has a negative sign. It doesn't affect its magnitude. Negative. When we talk for vector quantities, the negative sign indicates direction. We are not so concerned about the direction right now. It's not an issue. What we are concerned about is its magnitude. So we've been given our force function here to be equal to 5x. Okay. Now x is in centimeters. So what is the work done against the spring in displacing the mass, right? So we are now looking at another scenario, trying to get the work done when that spring is displaced from -1 to 2. So of course you remember your formula for work done. That's over an interval a to b, integrating the force function. That's basically it. So we are trying to we are going to integrate this force function 5x. We are going to be integrating it over the interval -1 to 2. That's simply what we are going to do here. So without much ado, we can just come here. This gives us 5/2 x squared. Okay, integrating it over the interval -1 to 2. So our work done here, plugging in our boundaries, that will be 5/2 into -2 into 2 squared minus -1 squared. Alright. So the work done here will be equal to 5/2. 2 squared is 4. -1 squared is 1. So that's 4 minus 1 here, giving us 3. That's 5/2 times 3. 15/2. 15/2 is 7.5. So 7.5. Okay, a mass is attached to a spring and it has an equilibrium position of x equals to 0. This means that it is at rest at this point. And when displaced with position x, it exerts a restoring force of -5x dynes. Now, we see that the force here, right, in terms of x, the force function is -5x. In this case, the unit is dynes. Okay, so there are some things we need to clarify here. Why does it have a negative sign? Right? Why does force have a negative sign here? You see, when the spring is displaced, when it is stretched or when it is compressed, as a result of its potential energy, it tries to go back to its original position. It tries to go back to its original position, and because of that, it is working against the force applied. So that force that tries to take it back to its original position is usually opposite in direction to the force applied. That's why it has a negative sign. The negative there just signifies direction. It's not really an issue because right now we are working with the magnitude. We don't really have issues with the negative sign here. All right. And also, what does dyne mean? It's very important we understand what this means because we would have to, it's the unit, so we have to express our work in terms of units too. Dyne here is remember Newton. Newton is actually kilogram meter per second. Right, but dyne here, dyne is an olden days of measuring force, olden days way of measuring force, and it is in grams centimeter per second. So you can see the distinction here. You can see the distinction here. All right. So we have our force function, and we are asked to find the work done. Now the work done is the integral of the force function over the interval a to b, where a and b are the positions of displacement. So in this case, w equals to the integral of 5x. Like I said, we are not worried about the direction there. We just pick out the magnitude from -1 to 2. So that's we're trying to calculate the work done in displacing from -1 to 2. And we have our force function. All right. So all we need to do is to integrate this. So that's going to be 5 over 2 x squared. Okay, over the interval -1 to 2. So to complete it, we have to substitute -1 and 2 into x squared and subtract them. So work done equals to 5 over 2. Right? So we factorize 5 over 2. Now plug in our boundaries as x. So that'll give us 2 squared, right? Minus -1 squared. Remember, you could have just plugged it in, plugged it in the signs like 5 over 2 times 2 squared, right? Minus 5 over 2 times -1 squared. But if you did it that way, you'd still get the same thing as this, right? But this is kind of easier. It's simpler, right? Because we would have already, because it's this is a simpler version because we have factorized 5 over 2 out already. So just working with this. And this is in situations where you do not have a calculator to work with. So it's ideal to make your work simple. So 2 squared is 4. -1 squared is 1. So W here equal to 5 over 2, that's the work done, times 3. 5 times 3 is 15. 15 divided by 2 is 7.5. So our work done is 7.5. And the question is, what unit are we going to use? our force is in dynes. If our force were in Newton, then joules would have been in order. But now our force is in dynes, so what are we going to do? And take notes, right? Take notes that our x is measured in centimeter, right? X is measured in centimeter. So that was why we could plug it in, because our force is in dynes. Our force is already in terms of it's already in centimeter, right? If our force were in Newton, we would have had to convert from centimeter to meter. But since our force is already in dyne, we just plug it in because the units correspond. So when our force is in dynes and our length is in centimeter, we are good to go. But the work done will no longer be in joules. It will be in erg here, ERG, right? And if you want to convert that to joules, all you need to do is to multiply it by 10 raised to power negative 7 here. Multiply by 10 raised to power negative 7. So our work done equals to 7.5 times 10 raised to power negative 7 joules. 1 joule equals to 10 raised to power negative 7 erg. So this is basically it, right? Nothing. It's you have your force function, plug it into it. If you don't have a force function, you might have to look for it. But in this case, we have been given our force function, so we are good to go in that regard. Plug it in, integrate it over the interval, and we're good to go.